is in Russia. So let me start the presentation. I aim to talk for about 50 minutes and give you 10 minutes for questions at the end. And this is the title of the presentation. It's a kind of overview, hopefully without too much jargon, and I'm not assuming too much prior knowledge on the topic, but I'm going to talk about past sea level rise. That's over glacial interglacial cycles, roughly the last million years of Earth's history. I'm going to focus a little bit on the instrumental record, which goes back about 150 years, talk about changes that have been taking place in the last few decades that we've measured from satellites, and then a little bit about what we think the ice sheets, what sea level is going to do over the next, focusing roughly on the next century up to about 2100, but that's the main focus. My name is Jonathan Bamber. I'm a glaciologist, a professor of physical geography, University of Bristol here in the UK. So I thought I'd kick off with a very brief explanation of what the sources of sea level rise are. And this is a figure that's taken from the one of the IPCC reports. I think it was the fourth assessment report published in about 2003, I think. And you can see there are various sources. On the left here, hopefully you can see my mouse. On the left, we have changes in terrestrial water storage. So those are ground reservoirs, aquifers, like ancient fossil aquifers, man-made reservoirs like dams and so on, and changes in land surface hydrology, which may be natural or may be anthropogenic or man-made. We have what's called vertical land motion, displacement of the land due to subsidence or even uplift because of something called glacial isostatic adjustment. It takes place over thousands of years when the ice sheets sort of recede from their maximum. That's a relatively small effect. We have changes in ocean circulation. Again, so changes in ocean circulation, they have an effect on the regional sea level, but if you integrate over the whole oceans, the net effect is zero because all you're doing is redistributing the water around the surface of the oceans. You're not making it any bigger or smaller through that. But then these two processes on the right here, which are in these red circles, are the ones that really are dominant. They by far and away have the largest impact on contemporary and past sea level changes. That is, the first one is as oceans warm, the water expands. That's called, that's the thermosteric effect. That's the changes in volume of the oceans due to changes in ocean heat content. And of course, you know, oceans can cool as well, in which case the sea level will go down. And then on the right, we have what's called the barostatic effect. That's the contribution to the oceans from changes in mass on land. And in particular, the most important change is melting of glaciers and ice sheets. And that's what I'm going to spend quite a bit of time talking about in the next 45 minutes or so. So these two, thermosteric and the barostatic or mass contribution to oceans, are the ones that are really by far and away the most important to consider on long time scales and also over the next century. Why do we care about sea level rise or sea level change? Well, this is quite an old plot, but it shows what are called megacities around the world. Not all of them, but some of the bigger ones. And a megacity, based on UN definition, is a city with a population of more than 8 million people. And many of these megacities are located in coastal areas that are vulnerable to changes in sea level. And a very recent estimate, this paper that I've cited here right at the bottom, which is what's called open access. Anyone can read it. Go to the journal and read this paper. And by the way, this paper was published in about, I think, December 2019, and it's already had over 400,000 views. It's a really, really important piece of work. And what they showed in this study is that for a 2-meter sea level rise, that's relative to today, so that's 2 meters of increased sea level, something like 600 million people will be not necessarily displaced, but will be flooded on an annual basis with the 2 meters. That's about 1/10 of the population of the planet. So sea level rise is an incredibly serious impact of climate change. We know as you warm the planet, the oceans are going to warm, you're going to get thermal expansion, and you're going to start melting ice. And so you're going to get a contribution from glaciers and ice caps around the world. So that's why it matters. And that's why we're particularly interested in, well, partly in what happened in the past, but especially how that might inform us about what might happen in the future. And so I'm going to spend a few minutes just explaining to you what we know about past changes in sea level. And this figure here that shows the Northern Hemisphere. So we have North America here at the bottom. This is Greenland. This is Northern Europe and Eurasia here. You have Russian Federation all around here. You can see that, and this is a plot. The blue shows the extent of ice cover at something called the last glacial maximum. That's the last time that we had very extensive ice cover over the planet. And that was about 20,000 years before present. And what you can see is that we had an ice sheet covering almost all of North America called the Laurentide ice sheet. It was actually the largest ice sheet in existence at that time. The Greenland ice sheet has expanded somewhat, and we have an ice sheet that's covering most of Northern Europe and parts of Eurasia. Actually, not that much of an increase in ice cover over Siberia, interestingly. A little bit of an increase over parts of Alaska, but the two biggest changes are the Eurasian ice sheet and the Laurentide covering North America. So that was LGM 20,000 years ago. This plot here shows changes in ice volume measured from, these are from marine sediment cores, over about the last 1 million years. And so we're going from the right-hand end of this plot is 1 million years ago, and the present day is at the left-hand end. So if we go from right to left, that's going, if you like, forward in time. And what you see, if you focus on the blue line here, the one that goes up and down very dramatically, that's showing changes in sea level, relative sea level over time. And what you see is that when it's very low, let's look at this minimum at about 600,000 years before present. Sea level at that time, this was a glacial, was about 130 meters lower than the present day. And that's due to the growth of the ice sheet over North America and Eurasia, and the expansion in extent of the Antarctic and Greenland ice sheets at that time. And so we had a lot of ice cover, 130 meters of sea level equivalent, more than we do present day. And if you look at this point at about, well, 630,000 years BP, and then you follow it forward in time to the minimum, you see that about 610,000 years BP, we're at an interglacial when global sea level was about minus 20, about 20 meters lower than present day. And we have a very rapid increase in sea level over about 10,000 years to an interglacial, a warm period like the one we're in today. And then if you carry on, you see that there's a fairly typical sawtooth pattern where you have a gradual decrease in sea level over a period of about something like 100 to 150,000 years to a new minimum, and then a very rapid increase. And that's very typical of glacial interglacial cycles. What that's showing us is that it takes a very, very long time to grow these ice sheets. Tens of thousands, in fact, 100,000 years to reach their maximum extent, but you can get rid of them very quickly. These huge expanses of ice can be removed in over a period of about 10,000 years. So if we then go on to look at the last 20,000 years or last 24,000 years since the last glacial maximum, that's here at about 20,000 years before present, you can see that sea level was about 120 meters below present day. And over time, it increased to about 8,000 years ago when most of the ice sheets that did exist at that time have completely disappeared. In particular, the ice sheet that covered North America had completely vanished by about 8,000 years BP. Now, this is a reconstruction from various different kind of proxies of relative sea level. And if you look at the mean rate of sea level rise from, let's say, about 16,000 years ago, when deglaciation really started to take place, to 8,000 years, it was about 1 centimeter a year. So that's equivalent to 1 meter in a century, which is quite a lot. It's a lot more than we're experiencing today. But you know, it's not completely beyond what we can cope with as a society in terms of responding to and adapting to. But there's this event at about 15,000 years BP. It's a very famous event in the sea level record called Meltwater Pulse 1A. And over a period of about 300 to 400 years, sea level rose at a rate that's 4 times larger than the mean over the deglaciation, at about 4 centimeters a year. That is 4 meters a century. And that happened over about 300 to 400 years. So we saw an increase of about 16 meters in sea level over that time. What that tells us is that the ice sheets can do really scary, dangerous things. They can lose mass incredibly rapidly as they're decaying, as they're melting, and they can produce rates of sea level rise of 4 meters a century. So that's what happened since the last glacial maximum about 20,000 years ago. This is a plot from another really important, interesting paper, which is a record from different kinds of paleo observations of sea level, of sea level variability during what's called the common era. So this is about the last 2,500 years. This top plot here, this black line, shows our best estimate of changes in relative sea level since about 2,500 years BP up to the present day. And these light gray lines show our uncertainty in these estimates. And one of the most striking things, I mean, the main take-home message from this plot is that the rate of sea level rise, that's in the last century, that's over here, 1900 to present day, it's at the right-hand end here. The rate is faster than we've ever seen over the last 2,500 years. And the absolute value where we are today is higher than we've ever seen over the last 2,500 years. So that's a concern for most climate scientists on its own. And then the bottom figure here shows a reconstruction of surface air temperatures. And you can see that, well, there's some variability in sea level rise on the top here, but you can see that certainly since about 1800, the changes in sea level are mirroring the changes in global air temperature very closely. Now I want to focus on what we know about what's called the instrumental record, and that goes back to around about 1860 roughly. And the record starts with a small number of tide gauge stations, mainly located around the northern hemisphere, because that's where most of the land mass is. There's not an awful lot of landmass in the southern hemisphere where we actually have tide gauges. So the sampling isn't particularly uniform everywhere around the world. And the vertical bars show our kind of uncertainty in changes in global mean sea level. And you can see that they're very high at the beginning of the record, but as we get more tide gauges over time, particularly sort of in the early 20th century, the uncertainties go down, and then from 1950 onwards, we have a pretty robust reconstruction up to 1992. The green line here is our record from satellite data, and that has the best accuracy, but it's also the shortest record. It starts in about 1992, 1993, and actually it only goes to 2005 here, but we have a record carrying on to 2020. We have continuous observations from satellite data. And so one of the things you see is that in the early part of the record, the rate of sea level rise is about just under 1 millimeter a year. Doesn't sound too bad, but it already between 1950 and 2000, it's accelerated. It's increased by about 50%. And actually the most recent data, and this is, we're confident this has nothing to do with the change in observing system that we're using, but for the last 25, almost 30 years, the rate of sea level rise has been about 3.2, 3.3 millimeters a year. So it's double the rate for most of the 20th century. So we're seeing a pretty clear acceleration in sea level rise over the instrumental record. This plot shows, the red line shows the total sea level rise as measured by satellite radar altimetry. Radar altimeters measure changes in surface elevation very, very accurately with a kind of millimeter accuracy. And so over a period of time, you can get incredibly accurate measurements of changes in surface elevation of the oceans. That's the total since 1993 to 2006. And the blue line here is the contribution, our best estimate, the contribution due to thermal expansion of the oceans, the thermospheric effect. And you can see that it counts for about 1/3 of the total rise. In fact, if I show you the linear fit through those lines, and there are some ups and downs due to things like El Nino sudden oscillation due to oscillations in the climate system that take place over a few years, and decadal oscillations. The fit for the total is 3.2 millimeters, and about 1/3 of that is due to thermal expansion. That means that the remainder must be due to, mostly due to melting of ice. So ice melt is really important for recent sea level rise, and even more important for our estimates of what we think sea level is going to do over the next century. So that brings me on to a little bit of background and context about about ice on the planet today, not 20,000 years ago, but where the ice is around the world as of 2020. And for that, I'll just introduce a little bit of geography. After all, I'm in a geography department in Bristol, so I thought that would be appropriate. The plot on the right shows, this is obviously the northern hemisphere at the top, southern hemisphere at the bottom. And this plot, the yellow areas are what are called glaciers and ice caps around the world. That's everything that is not covered in the ice sheets that cover Greenland and Antarctica. They are, if you like, a separate category because of their huge size. The yellow is glaciers and smaller ice caps. The white area, this is Greenland here, and we have Antarctica in the southern hemisphere here. Now, the geography of these two regions is very different. The Arctic Ocean is an almost landlocked ocean, and it's the smallest in the world. And Greenland is part of the landmass that actually isolates the Arctic Ocean from the rest of the climate system. And it has a relatively maritime climate. In other words, it's relatively warm, relatively wet compared to Antarctica. In Antarctica, we have completely the opposite situation. We have a continent that is surrounded by an ocean. And actually, Antarctica is surrounded by the biggest ocean circulation, ocean current in the world, called the Antarctic Circumpolar Current, which effectively isolates the continent somewhat from the rest of the climate system. And as a consequence, Antarctica is actually one of the driest, most arid, coldest, well, it's the coldest continent in the world, but it's also one of the driest continents in the world. So in the interior of East Antarctica, that's this bit over here on the right, the annual precipitation is in some places about 3 or 4 centimeters a year. That's equivalent to some parts of sub-Saharan Africa. So very, very different climate and geography related to Antarctica and Greenland. Now this figure, what I'm showing here are what are called digital elevation models. These are representations of the topography of the ice sheets. This is Antarctica to scale. That's Greenland on the same scale. That is the European Alps, because that's the kind of ice that's closest to me. And well, there's the UK down the bottom. And just for all of you, I thought I would include a map to the same scale of the Russian Federation, roughly, approximately. It's not meant to be that accurate, but it just shows, I mean, Russia is a huge country, but it's dwarfed, even Russia is dwarfed by the size of Antarctica. Antarctica is a huge continent. It has an area that's larger than the conterminous USA. It's about 1.5 times the area of Australia. And the ice in the interior of Antarctica is almost, in places, it's almost 5 kilometers thick. So it's an incredibly big piece of ice. And just like in Western Russia, the weather might, or the climate might be changing in a somewhat different way to Siberia in the Far East. It's exactly the same for Antarctica. Parts of Antarctica are influenced by the Pacific Ocean, other parts by the Indian, and other parts again by the Atlantic. So it's a huge continent that may not be feeling the same kind of changes in climate everywhere around it. So one other thing I should say about Antarctica is that it's usually described as 2 ice sheets. The one on the left here is called the West Antarctic ice sheet. It's much smaller, but we believe it's much more vulnerable to climate change than its larger cousin on the right here, which is the East Antarctic ice sheet, this big one on the right. So something like somewhere between 80 and 90% of the total freshwater store of the whole planet is locked up in the Greenland and Antarctic ice sheets. It's a 99.5%, so almost all of the ice on the planet, that's not freshwater, but all of the frozen freshwater, all of the ice is contained in the 2 ice sheets. If we melted the Greenland ice sheet tomorrow, we would raise global sea level, this SLE stands for sea level equivalent, global sea level by about 7.4 meters. If we melted West Antarctica, the number is 4 meters, East Antarctica, 53. So it's almost an order of magnitude bigger in terms of its sea level contribution than either Greenland or West Antarctica. It is really like a huge ice mass. And glaciers and ice caps, everything else outside of the ice sheets is less than 0.5 meter of sea level equivalent. So just going back to this plot I showed earlier, where the gap between the red and the blue line is due to melting ice, I thought I would show you what we know about what's happened to land ice, because it has been the biggest contribution to sea level over the last 30 years or so. Right, so this is a really busy plot. There's a lot of lines on it and it's very noisy. Each circle, each dot here is 1 year of observations. And this is from 1992, when we have the start of our reliable satellite record. And it actually continues to 2020, but in this particular study that we published a couple of years ago, we only made the results up to 2016. The black line is all ice on the planet. It's glaciers, ice caps, and all of the ice sheets put together. And what you can see is that in the early 1990s, and the y-axis here, let's look at the right-hand side, is in sea level equivalent, millimeters of sea level. And what you can see that in the early 1990s, there's a lot of interannual variability, but the contribution from all ice was relatively small. I mean, it did get up to a millimeter a year in about 95, but then it was slightly positive in 96 and so on. But over time, it's become increasingly negative, or the contribution has become larger, if you like. And then, you know, we've got a number of noisy plots for East Antarctica, West Antarctica glaciers in Greenland. What I've done here is I've tried to reduce the interannual variability so that each dot, each colored dot now represents a 5-year mean estimate for East Antarctica in green, West Antarctica in blue, glaciers in purple, Greenland in red, and the total in black. And it's quite clear when you look at this that, okay, there are still some fluctuations, but when you integrate all of these together, the contribution from land ice has been increasing such that by the last decade, it has been about 2 millimeters a year. So how do we know what the ice sheets and glaciers and ice caps, for that matter, have been doing over the last 25 or 30 years? I mean, where do all these numbers come from? How on earth do we know? Remember that the Antarctic ice sheet is you know, twice the size, 1.5 times the size of Australia. It's a huge area. It's very remote, very cold. We can't really make observations on the ground over the whole of Antarctica. That's just not practical. So what we have to do is use satellite technology. And, you know, that our reliable coverage from satellite data of Antarctica and Greenland only goes back to about 1992. Now, I mentioned radar altimetry earlier when we were talking about measuring changes in ocean sea level. Well, you can use the same technology over the ice sheets. You get, it's not quite so accurate, but you can basically measure the change in height, the change in elevation of the ice sheets. And from that, if you integrate it over the whole of Antarctica, Greenland, then you can estimate the change in volume and the change in mass. So that's one approach. Actually, in 2002, NASA launched the first ever satellite laser altimeter mission. Basically the same concept, but rather than using microwave energy, it uses laser, you know, visible light bouncing off the surface. And it's a more accurate approach than radar altimetry. And in 2019, they launched the second laser altimeter mission called ISAT-2. But we also have some other technology that uses changes in the gravity field of the Earth using 2 satellites in a mission called GRACE. And GRACE stands for the Gravity, Recovery, and Climate Experiment. And I'll just say a little bit more about GRACE. This is a movie, kind of animation, like a artist's impression of what the 2 GRACE satellites look like. Basically, what they're doing is they're flying over the surface of the Earth, the 2 satellites, at an altitude of about 500 kilometers. They're separated from each other by about 200 kilometers. And as they fly over the surface of the Earth, there is a microwave ranger, this sort of light colored beam between the 2, that is measuring the distance between the 2 satellites to an accuracy of a few microns. That's less than the width of a human hair. It really is incredible technology. And as they fly over, and the first satellite gets close to an area of, let's say, high density rock or a mountain range where the gravity field is a little bit more. That first satellite, it gets pulled towards the Earth faster than the second one. And so it accelerates away from the first satellite. And so the distance between the two changes with changes in the gravity field of the Earth. And just these tiny, less than a millimeter change in distance between these two satellites as they fly around the surface of the Earth gives us incredibly detailed information about changes in the distribution of water and ice on the surface of the Earth. And so from this mission and its successor that was launched last year as well, we can get really unique observations about changes in the mass of Greenland and Antarctica, but also hydrology, global hydrology as well. So this is an example of what the elevation changes from the ISAT laser altimeters looks like over Antarctica on the left and Greenland on the right. Now let me I'm just going to make sure that if you have, oh, okay. Oh, okay. Oh dear, I seem to have, I shouldn't have done that. Something, oh dear, something's happened to my sound now. All right, okay, I think it's good. What I'll do is no, I think, yeah. Let me sorry, little hiccup. I just wanted to make sure the sound was okay. If I mute that, that should do the trick, I think, and go back to hopefully it's all good now. Sorry about that little hiccup. Anyway, so this shows elevation changes over Antarctica and Greenland over about a 16-year period. Actually 17 years in total, because it includes 2019. And it's important to notice, so red shows areas of thinning, in other words, mass loss, and blue shows areas of thickening or mass gain. But if you look at this scale here, it's not linear and it's not equal on both sides. So the blue goes up to a total of plus half a meter, whereas the purple red here is up to minus 10 meters. And you can see that there are some changes here that are almost 10 meters of thinning over that period. Whereas the blue, you know, the maximum, well, over the interior of Antarctica, it's maybe just a few centimeters. So we have some significant areas of thinning in West Antarctica. That's this area here. And also along this section here, which is called the Antarctic Peninsula. But most of East Antarctica, which is the biggest ice sheet on the planet, we're not seeing any really big changes. A little bit of thickening, but certainly not enough to compensate the losses in West Antarctica. If we look at Greenland now, the picture is a little different. Here we see the classic signs of climate change or global warming. So what we have is a little bit of increasing elevation or mass gain in the interior because we have slightly increased snowfall, but very dramatic thinning, really substantial thinning all around the margins of Greenland, due to mainly due to increased surface melting. That is, if you like, a classic fingerprint of an increase in temperature over the Arctic over the last 20 years or so. This is from a very recent paper that was only published about a month ago, I think. So some really worrying signs in the ice sheet, and these trends are from all our analyses and the plots I showed you. Both trends in West Antarctica and Greenland are accelerating over time. So that's a little bit on how we make observations of ice sheets, and we use the same technology for glaciers and ice caps as well. I just didn't show any of the results from those. Another thing to be very aware of is that changes in sea level, that the sea level, I've called it sea level rise here, but let's changes in sea level is not uniform around the world. The top plot here is an estimate of global sea level change over a 50-year period. So it's not, none of that, all the interannual variability has been averaged out. This is over 5 decades, but you can see that there are some areas that are increasing well above the global mean, and even over a 50-year period, we have some areas in the Western Pacific here, just north of Australia, where sea level has actually been going down over 5 decades. And then if we look at the last decade, we have a really large increase in sea level rise over the Western Pacific. So a change from the 50-year mean, which is as much as 15 millimeters a year. That is about 5 times larger than the global mean. And over the Eastern Pacific, on the, let's say, the western seaboard of the United States, we actually have sea level lowering. And these variations in global sea level, the fact that it's not all going up uniformly, are due to 2 key effects. One is ocean circulation, changes in ocean dynamics, and variations in absorption of heat by the ocean, so the changes in ocean heat content, which are not uniform around the world. And the second effect is quite a difficult one to explain, but it's really a fascinating, an unexpected, almost counterintuitive characteristic of changes in the gravity field of the Earth that affect global sea level. This is what's called the gravitationally consistent change in sea level due to melting of ice over the last decade. Well, between, roughly the last decade. And the green line is the global mean. That's the kind of average contribution from melting ice over this time period. The area in blue is actually showing areas where sea level has gone down. And what's counterintuitive is that you can see that around Greenland, which I just showed you has been melting and contributing to sea level over this time period, sea level has gone down due to this gravitational effect. And the reason for that is that you have a lot of ice on the Greenland ice sheet that's on land. And that increases gravity around Greenland. So because the ice is on the land, the strength of gravity is a little bit higher there, and that pulls the water towards Greenland because the water is responding to changes in the gravity field. The surface of the ocean follows variations in the Earth's gravity field. And if you melt ice on Greenland and you put it in the ocean, well, you reduce the strength of the gravity field over Greenland. And that means that the water is not being pulled towards Greenland so much, and sea level actually goes down. And that's called the self-gravitation effect. And so you can see that's also happening around Antarctica. And what's interesting or kind of, if you actually problematic about this effect is that, so in what's called the near field, close to the areas of mass loss, sea level goes down, but in the far field, many thousands of kilometers away from the areas of melting, particularly at low latitudes, and particularly here in the Pacific, sea level goes up by more than the global average. And this is in areas, let's say in the Western Pacific, where you have a lot of island atolls, which are particularly vulnerable to sea level rise. So these are examples of what are called sea level fingerprints. This is the effect of changing gravity field due to melting of Greenland up here on the left, Antarctica on the right, and Alaska and glaciers and ice caps here. It's a really interesting, but as I say, counterintuitive effect of melting ice. So in the last few minutes, I'll say a few words about projections. So it's really important because we have to understand and know how sea level is going to change over the next 100 years so that we can adapt to those changes. When you're building, let's say, a power station, it doesn't have to be a nuclear power station, but if most nuclear power stations are located in coastal areas because they need a huge water supply. And nuclear power station, it may take 20 years to build. It might be active for, let's say, 50 years, and it might take another 20 or 30 years to decommission. So we're looking at about 100-year timescale for these kind of major built infrastructures. And so we need to know, we need to have estimates of what sea level rise regionally is going to look like over a century timescale. It's absolutely vital for city planning, for maybe even moving populations, as they're doing, for example, in Jakarta, away from areas where flooding is going to become a problem. But it's very difficult to do. Now we understand how thermal expansion of the oceans works, you know, and we have pretty good estimates of as the climate warms, the atmosphere warms, how heat is going to be absorbed by the oceans. And so that's something that we can model quite well. The big uncertainty is, what are the ice sheets going to do? Now, I'll just go back a little bit. And I showed that example of that event called Meltwater Pulse 1A, about 15,000 years before present. And in that example, we saw that, you know, the ice sheets, they can do pretty scary things, 4 meters a century. But that was when we had an ice sheet partially covering North America. What about Antarctica and Greenland today? Can they do similar sorts of things? That is the $64 million question. And it's a very difficult one to answer. Now, this plot, it's quite complicated, and I've even copied the full description underneath here. Don't try and read all the words. It's from the Intergovernmental Panel on Climate Change, the IPCC Special Report on Oceans and Cryosphere, the SROC, which was just published only a few months ago in 2019. And it's from chapter 4, which deals with sea level. And it's freely available. You can download it from the IPCC website. All the chapters are free to view. But there's two. So the blue line is a projection of the climate. It's called RCP 2.6. What that means is that's a future climate where we do as much as we can to mitigate carbon emissions over the next century. And actually, we take really pretty drastic measures to reduce carbon emissions. And under RCP 2.6, temperatures increase a little bit, but then they stabilize below 2 degrees above pre-industrial. And in that scenario, you can see, if we look at this blow up for 2100, you can see that the projection of sea level rise for this strong mitigation, climate mitigation scenario is about 40 centimeters, the median, but there's a little bit of uncertainty. This blue shading indicates the uncertainty. If we look at the red plot, the red curve here, that is for a future climate scenario where we do nothing. We just carry on our current trajectory, which results in a global warming by 2100 of about 4.5 degrees above pre-industrial. In that case, sea level rise can reach up to about 1 meter. The median, that's the solid line here, is a bit less. It's about 60, 70 centimeters. But the uncertainty, the one standard deviation uncertainty, exceeds about 1 meter. If you go out a little bit further to 2300, so that's, you know, a 3-century estimate, the uncertainties become absolutely huge. And, you know, 300 years in the history of humanity is not so long, actually. But we're looking at, in this business as usual, this pretty, you know, scary climate change scenario. We're looking at a best estimate of sea level rise of about 3 meters. 3 meters means that, you know, Bangladesh has pretty much completely disappeared. Bangladesh has a population of about 170 million people now. The Netherlands will disappear, the Nile Delta, many, many coastal areas, Shanghai, and so on. You know, 3 meters is a really, really kind of scary number. But you can see that the uncertainty is about plus or minus 2 meters here. And that all comes from our uncertainty in the ice sheets. Now, those estimates that I just showed you are from model projections, but we carried out, but models, it's very difficult to estimate the uncertainty, the spread in models. And although they try to do it in the IPC, it's very challenging to do. We undertook very recently and published just last year a paper where we took a very different approach. Something, the details don't matter, it's called structured expert judgment. And what I want you to do is just focus on this figure here for 2100. The y-axis is a probability, a likelihood of a value. So these curves are what are called probability distribution functions, PDFs. The blue curve is for like a moderate warming, 2-degree kind of warming. And the red curve is, you know, like the red curve I just showed you before, 5-degree warming by 2100. And the peak is the modal value. So that's the kind of most likely estimate. And you can see here that actually, if we take the 2-degree warming, and this is just for the contribution of the ice sheets to sea level, we get an estimate here that's, oh, it's about 25 centimeters, something like that. And the median, which is a bit higher than the mode here, is 51 centimeters. It's this value here. But what I want to emphasize in this plot is that these curves are not, they're not bell-shaped. In other words, they're not Gaussian, they're not a normal distribution. They don't have that symmetry around the median. And in particular, when we get to warmer climates, they are very asymmetric, and we have what's called a long upper tail. This long upper tail means that there is a low but significant probability of actually very high sea level estimates. And in fact, we in our study, we found that there was a 5% probability. So that's not so unlike that. So 1 in 20 chance for this really hot, you know, this 5-degree warming world, of a contribution of the ice sheets of about 180 centimeters. Now, if you add glaciers and ice caps and thermal expansion, that takes you to over 2 meters by 2100. So that was one of our key findings. Now, it's for the worst case climate warming, but nonetheless, remember my statistic from earlier on? You know, a 2-meter sea level rise will affect something like 1/10 of the population of the planet. So I will wrap up there. I think that's pretty much exactly 50 minutes. And I have some 5 take-home messages, which I'll just run through very quickly, but I'm just kind of reminding you of some of the key things that I said earlier. So one thing we know is that sea level is rising faster, and it's higher than it ever has been in the last 2,500 years. It's a major threat. It's one of the most serious consequences of future climate change. The ice sheets since the mid-1990s have become a major contribution to sea level rise, and that rate is accelerating and increasing with time. They have the biggest potential contribution to future sea level rise and the biggest uncertainty around what they might do. So that's my point number 5. But But I think that the last thing that I really want to, the last point I really want to say is that, you know, and it's really obvious, I know, but if you warm the planet, ice will melt and sea level will go up. So thank you very much for attending. I'm going to stop the presentation there, and I will stop sharing my screen so that you can see me and this beautiful picture of Elbrus and the Caucasus in the background. And I will now see, let's see if we have any questions. So I can see in the chat some questions. Shall I think best thing, I'll take the questions here. So from Cambridge English, St. Petersburg, one question, not a scientific one, but still, what's the most beautiful place on earth you've ever visited? Well, that's a really lovely question. Wow. You know, I love the mountains. I got into glaciology because of my passion for mountaineering and being in the mountains. And I was in Nepal in 2018 in the Everest region, and really it was close to a mountain called Amadablam, which I thought was really absolutely stunning. And what's so spectacular about that area of Nepal is that it's very dry and quite arid below the mountains, and then you have these beautiful majestic peaks above. And then Elena asks, what do you think we're going to face after pandemic? Humans are using lots of face masks and they are all going to the ocean. How do you think it will affect the speed of increasing sea level? Well, I don't think that ocean pollution, you know, let's say plastic in the oceans or face masks or any other things like that, it's a very good question. That won't really have much impact on sea level rise. It will certainly have probably a pretty serious impact on the ocean ecosystem, which is already being very seriously impacted by plastic in the ocean, but not so important for sea level. Next question. I want to ask about the pandemic. So this is from, oh, I'm sorry, his name is in Russian and I'm afraid my Russian's not so good. What do you think? Will we face any such things in the future? Maybe not the virus, but some serious climate changes. Well, you know, we've known about the damaging consequences of climate change for a long time. The IPCC has been publishing its reports. It's been in existence for over 30 years now. And the message hasn't really changed. That is that if we don't take pretty drastic action to reduce carbon emissions, then there are going to be some very serious, actually very unpleasant consequences of climate change. And unfortunately, I think that we're already starting to see some of those. You can't attribute a single event, like a single hurricane or, you know, a single summer of forest fires in Australia to climate change, but you can certainly assess their probability of happening in a warming world. And colleagues, my climate science colleagues have done that. And it shows that, you know, things like forest fires, increased intensity of hurricanes, more tropical storms, sea level rise, water security issues, and droughts are all going to be, you know, some of the serious consequences that we are going to face, irrespective of how we try and mitigate against the worst consequences of climate change going forward. So I think we're already seeing some of the effects, and they unfortunately are going to get worse. Having said that, you know, that sounds really negative, but I think there's plenty we can do to make it less bad. Yeah, okay, some bad things are going to happen, but the more we do now, the less bad things will be in the future. So I think we must, as individuals, as citizens, but also as governments and businesses and corporations, we must do all we can to reduce the worst impacts of climate change going forward. So let me see if I have a couple of questions by email. No, okay, those are two that I've already had. So I think those are all the questions, unless anybody else has one that they want to bring up. Diana D says thank you. Well, thank you very much for inviting me. Look, I was really pleased to accept this invitation because I don't normally talk to this kind of community. I don't usually get this opportunity, and of course I love to talk about my science, so you know, it's been a real pleasure to do that. Elena asks, do you think now there is the way to at least slow the process of increasing sea level? Yeah, absolutely. That's a really good question. So I think we are locked in to some sea level rise, to a rate that is certainly above the rate that we've seen in the 20th century. That's because there are parts of the climate system where the inertia is very significant, and in particular the oceans. So the deep ocean circulation takes multiple centuries. So the heat that is being absorbed at the surface will take, you know, 1 to 2 centuries to reach the very deep ocean. And so I think we are locked into you know, some acceleration in sea level rise. Even I showed the example of the moderate warming, you know, less than 2 degrees by 2100. Remember that we're already over 1 degree now. Well, we're looking at about sort of 40 centimeters by 2100, something like that, 30 to 40. But if we take really bold action now, that those higher numbers, you know, estimates, a sea level rise of, let's say, more than 1 meter, can be averted. That's something that I'm very confident of, because there are thresholds in the climate system, there are thresholds in the ice sheets, which we really don't want to pass, because then we'll be committed to multi-meter sea level rise. And you know what? I think several people have talked about COVID, actually, the pandemic, and there's a really unique opportunity, I mean, a once in a lifetime, once in a century opportunity for all of us, for governments around the world to make the right decision coming out of this pandemic. And that is, governments around the world are looking to for an economic recovery, to try and reinvigorate their economies after the pandemic. Here in the UK, we're looking like something like maybe a 10% reduction in GDP, you know, really a major recession. The same in the United States, same in pretty much all countries that have been affected by the pandemic badly. And governments around the world have committed something like $20 trillion to economic recovery after the pandemic. Now, if they ensure that those $20 trillion go towards a green recovery, a just, fair and sustainable recovery of the economies, then I think we have a chance of avoiding the worst impacts of climate change. But if they make the wrong decision and they carry on investing in the coal industry, in fossil fuels, in digging up more oil and coal from the ground, then I think things are going to go in a really bad direction, and I really fear for the future of humanity. Let me see. That was Elena. And somebody else says, thank you, the webinar and your background are amazing. Well, look, thank you for joining. I hope you enjoyed it. And I guess that's an hour, so I should finish here. Yeah, look, I hope you found it informative and that there wasn't too much you didn't understand. And well, look, enjoy the rest of your studies, and I hope you stay safe and stay well. Okay. Goodbye.